Hello, everybody. Welcome once again to this new session of Frontiers in Mechanical Engineering and Sciences, which is a multi-university webinar series made possible by several participating universities, as you can see. So the main credit of this series goes to Professor Devesh Ranjan, the current chair of mechanical engineering at Georgia Tech. This was primarily his brainchild, and several of us from different universities helped him on this. So this has been going on for several semesters now, and today we have a very exciting lineup. The theme is Advances in Thermal Sciences, and we have two great presenters, Dakotah Thompson from University of Wisconsin-Madison and Tian Li from Purdue University. More about them would be discussed by our moderator today. Our moderator today, Professor Matthew McDowell. More about Professor McDowell. Professor McDowell is an associate professor at Georgia Tech with appointments in the Woodruff School of Mechanical Engineering and the School of Material Science and Engineering. He received his PhD from Stanford University in 2013 and was a postdoc at Caltech from 2013 until 2015. Professor McDowell has received numerous awards, including Presidential Early Career Award for Scientists and Engineers, PCAS, Sloan Fellowship, NSF Career Award, AFOSR Young Investigator Award, and the NASA Early Career Faculty Award. So without spending any more time, I would like to invite Professor McDowell to take up the stage and introduce the speaker and the theme of today's talks.
Yes, great. Thank you, Siddhartha. It's quite an honor to be introduced like that. I think the main focus should be on the speakers here today, of course. So we have two great early career investigators focused generally in the area of materials, thermal sciences and materials, as well as novel bio-based materials for engineering applications. So I'm very excited about these two talks today. I'll start with introducing Professor Thompson. He'll speak first. So Dakotah Thompson did his undergraduate at Georgia Tech, actually, where I'm a faculty member, and then did his PhD at the University of Michigan. And in his career, he's focused on nanoscale heat transfer and heat transfer mechanisms in materials. In his short career, he's already received a number of important awards and distinctions, including the NSF Career Award, I guess recently. So congratulations on that, as well as funding from the Office of Naval Research. And so, Dakotah, we're excited to hear what you have to say today, and go ahead and take it away.
Hey, great. Let me share my screen. Let's see. And then I will. Can everyone see that?
Yep, looks great.
Okay, let me get my laser pointer up as well. Okay. All right, well, yeah, thanks everyone so much for having me. It's a real honor to speak to today. So today I'd like to discuss some of my recent work studying radiative thermal transport. And I'll also discuss some emerging trends in this field at the end. So I want to start off though by motivating this research a little bit. Thermal radiation is central to a lot of technologies that we use every day. For example, thermal sources have, for centuries, been the main source of lighting that we use in our society. So an example of this is the incandescent bulb you see on the left. Now, these bulbs have recently been replaced with LEDs, but incandescent lamps are still central to a lot of infrared spectroscopy applications like gas sensing, which is kind of depicted on the right. In addition, thermal imaging is central to things like night vision cameras, which are important for military applications. as well as non-contact thermometry, which you can see on the right, which is an important diagnostic tool during the COVID-19 pandemic. If you look at the picture on the left, you can see a concentrated solar power plant in Spain, where essentially the radiant energy from the sun is collected and used to generate steam. The picture on the right shows uncontrolled thermal emission during steel production, which is a major source of waste heat. And I'll talk in later slides about a potential technique to actually recover this waste heat to generate electricity. And finally, thermal radiation is central to a lot of thermal management technologies, like the design of my vacuum flask on the left here, to the modeling of our planet's climate. So if you've ever taken a heat transfer class, you're probably familiar with the plot on the left. This is called the Planck spectrum, where the radiation intensity emitted by an ideal black body is plotted as a function of wavelength. Here you can see that the thermal emission from this black body is spectrally broadband, and it happens to be peaked at a particular wavelength, which depends on the temperature of the object. So if the object is close to the sun's temperature, the peak thermal wavelength occurs in the visible at around 500 nanometers. If the object is close to the room temperature, the peak thermal wavelength is in the infrared at around 10 micron. Now, the Planck spectrum is important because it gives us an upper limit to the maximum radiation intensity from any real object at a given temperature. It also gives us the maximum possible radiative heat transfer rate between any two real objects at different temperatures. Okay. So in addition to being spectrally broadband, thermal emission also occurs diffusely in all directions, which is sort of illustrated on the right here. So because of these characteristics, you can think of thermal emission as essentially the opposite of a collimated laser beam, okay? But this isn't the end of the story. And it turns out that Planck's laws are not completely general. And this is something that Planck himself acknowledged in his own textbooks. So it turns out that if the gap size between two objects or the size of the objects themselves are much smaller than that peak thermal wavelength, then Planck's laws are no longer valid. So let's look at one limit, which you can see illustrated on the left. What happens to the radiative heat transfer between these two surfaces when the gap size between them is very small? So longstanding theoretical predictions have suggested that in this near-field regime, the radiative heat transfer rate can actually be greatly enhanced above the black body limit. And this is illustrated if you look at the plot on the left, where the computed radiative thermal conductance between two planar surfaces is plotted as a function of the gap size. And this was done for various materials comprising the two surfaces. So as you can see, at room temperature, as the gap size is reduced below around 10 microns, you start to see these large enhancements in the conductance, which depends a lot on the specific materials involved. Now, these theoretical predictions are based on an alternative and more general framework for describing thermal radiation, which is called fluctuational electrodynamics, which I may abbreviate as FED in this talk. So the physical mechanism behind these large enhancements in the near field is sort of illustrated on the right. Here you have two bodies, one hot shown in red and one cold shown in blue. When the gap between them is very large, then heat transfer can only occur through propagating waves, which are emitted from the hot object and are absorbed by the cold object. When the gap size between these surfaces is very small, you can also have contributions to the heat transfer from evanescent waves or resonant surface waves, which decay exponentially outside of the surfaces, but can actually couple across that small gap. This is also referred to as photon tunneling. Now, despite these interesting theoretical predictions, experimentally studying near-field radiative heat transfer is technically very challenging. And for example, how do you practically achieve stable nanometer-sized gaps, right? Also, how do you eliminate other modes of heat transfer, like conduction through air molecules or surface contaminants, which could increase the uncertainty in your measurement? So on this slide, I want to show you a measurement approach I helped develop, which allowed us to overcome a lot of these technical challenges. So the approach relied on fabricating the two microcalorimeters that you see in these electron micrographs. The first device are called the emitter, and the device on the right are called the receiver. Each of these is comprised of silicon, and it's essentially a suspended structure that's supported by 4 long and thin support beams, which help to thermally isolate the structures. Each device also has an integrated thin film platinum line, which can be used to either heat up the structure or measure its temperature rise. Also, each of these devices has a planar pad, here false colored in red and blue respectively, which can be made to be extremely flat and extremely clean. So once fabricated, we were able to precisely align and parallelize these two devices in the configuration that you see illustrated below. And we were able to do this using a custom-built nanopositioner, which is shown in the picture on the right. Once aligned, we could then move these devices into a high vacuum chamber here, which is inside of this radiation shield. So under high vacuum conditions, we can essentially eliminate convection from the measurement. So the only heat transfer between these devices is due to radiation. Okay. So once in high vacuum, we could heat up the emitter by several degrees and then measure the temperature rise of the receiver. And we could do this while also systematically stepping the emitter towards the receiver until contact. And we could do this with a piezoelectric actuator, which allowed us to adjust the gap in steps of around 2 nanometers. Okay, so from these measured temperature rises, we could estimate the radiative conductance between the planar pads. So here you can see the central results of this experiment, where we plot the radiative thermal conductance between the pads as a function of the gap size. And in this experiment, both pads were comprised of silicon dioxide. So as you can see, we're able to sweep the gap from over 10 microns all the way down to around 55 nanometers before contact was established. And at the smallest gap size, we observed over 100-fold enhancement in the conductance compared to the estimated black body conductance, which is captured by the horizontal dashed line down here. Okay. Now, these experimental results also agreed quite well with our fluctuational electrodynamics formalism, which the predictions of that FED framework are captured by the solid green line here. Okay, so we do get good agreement. Now, the theoretical plot on the left is the computed spectral conductance between these two silicon dioxide surfaces as a function of frequency. And this is done for various values of the gap size. So for the smallest gap size that we simulated, 50 nanometers, you see that you get these large enhancements in conductance in 2 spectral regions, one here and one over here. And it turns out that it's in these spectral regions where surface phonon polariton modes are supported at the surfaces of these silicon dioxide surfaces. Okay, so because of that, it turns out that it's the coupling of these resonant surface modes that's responsible for the large enhancements in conductance that we observe. Okay. Now, we actually leverage these near-field effects in a follow-up experiment demonstrating thermophotovoltaic energy conversion. So a thermophotovoltaic device, or a TPV device, works the following way. Basically, you take a low bandgap photovoltaic cell, and then you can use that to capture the thermal emission from a hot object to generate electricity. Now, the conversion efficiency and power output of a TPV device is typically pretty low compared to a conventional PV device. But it's been proposed that you can actually enhance its performance using these near-field effects. And so if you could do that, it may be a good strategy for harvesting waste heat or low-grade waste heat from thermal sources. Okay, so in this experiment, I fabricated the emitter device that you see in this electron micrograph here. This is essentially a cantilevered structure that we can heat up by several hundred degrees to simulate a source of waste heat. Okay. The PV cell in this experiment is shown in the electron micrograph below. This is a commercial device. And so under high vacuum conditions, we were able to precisely parallelize the surfaces of the emitter and the PV cell in the orientation that you see here. And so after heating up the emitter by several hundred degrees, we could then perform IV sweeps of the PV cell in order to characterize its electrical power output. And we could do this while also stepping or systematically adjusting the gap size between them. So on this slide, you can see the central results of the experiment. Here, the emitter was at a fixed temperature of 655 Kelvin, and the band gap of the cell is around 0.35 EV. So on the left, you can see the IV sweep, the measured IV sweeps of the PV cell for various values of the gap size. What you'll notice is that as the gap size is reduced, the short circuit current and the open circuit voltage both tend to increase. So it says maybe my internet connection is a little bad. So if I break up, please let me know. But basically, yeah, so basically this indicates that the smaller the gap, the higher output, power output you can get. So on the right, we plot from these IV sweeps, you can get the maximum power point of the PV cell. And that's plotted on the right as a function of the gap size. So as you can see, as we reduce the gap size from around 10 microns to 60 nanometers, we see a 40-fold enhancement in the electrical power output compared to the far field power output. And this result also agrees quite well with the FED framework, which we use in combination with a detailed balance of the PD cell. Okay. So at this point, I want to kind of transition away from talking about this near field regime, and I want to talk about the opposite limit. Okay. So what happens if you have two objects that are far apart, but the dimensions of the objects themselves are small? So in contrast to this near field world, this opposite limit has been far less studied. So on this slide, I want to show you a measurement approach I developed that allowed me to quantitatively measure the radiative heat transfer rate between two individual nanostructures. And so the approach relied on fabricating the two suspended nanomembranes you see in this electron micrograph. Both of these membranes are comprised of silicon nitride, and they're suspended by 4 logarithm support beams. These membranes are also coplanar with one another, and they're separated by a fixed gap of 20 microns, which ensures that they're in the far field of one another at room temperature. And that ensures that no evanescent waves can contribute to the heat transfer between them. If you look at the inset, you can see that each of the membranes has an integrated platinum line as well, which can be used to heat up the emitter, here false colored in red, and measure the temperature rise of the receiver, here false colored in blue. So to investigate the effects of small dimensions on the heat transfer, I fabricated different sets of these devices with various thicknesses, which ranged from like 11 microns thick all the way down to 270 nanometers, which is much smaller than that peak thermal wavelength. So here you can see the central results where we plot the measured radiative conductance between the emitter and the receiver as a function of their thickness. So the basic trend is that as the thickness drops, the conductance drops as well. And this is sort of, I think, what you would naively expect, or at least what I expected initially. What's interesting, though, is when you compare this to the estimated black body conductance between the devices, which here is captured by the dashed line. So this black body conductance was accurately estimated using a finite element model, which accounted for the exact geometry of the membranes, including their support beams, and it basically assigns an emissivity of 1 to each surface. So as you can see, for the thickest membrane, the measured conductance and black body conductance actually agree quite well. But there starts to be large deviations between these two curves as the thickness drops. So the red curve here plots the ratio between these two curves for each thickness. And for the thinnest membrane, which is 270 nanometers thick, you can see that the black body conductance underestimates the measured conductance by over 2 orders of magnitude. So initially, this result was very surprising to me, and I was initially pretty skeptical because these large enhancements in heat transfer in the far field had never really been demonstrated before. And so that led me to perform a number of very painstaking control experiments, which you can read about if you're interested in the SI of this paper. But basically, from doing those, it led me to the conclusion that this was not just some measurement artifact. So then the question became, well, can this be explained? And if so, what's the mechanism behind these enhancements? So to answer the question, we again relied on our FED formalism, which we implemented using a boundary element method, which you can see illustrated on the left. That allowed us to essentially simulate the exact geometry of our membranes. And from that, you can see the plot on the right, where the predicted conductance based on the FED framework actually agrees quite well with the measured results for each thickness. So clearly, the measured results do make sense under the FED framework. The question then becomes, what's the mechanism? So it turns out that we get these large enhancements in heat transfer due to the specific shape and orientation of the nanomembranes. So because of their high aspect ratio, these membranes are similar to a slab waveguide, illustrated on the left here. So any slab waveguide can support what are called guided modes, which are electromagnetic waves that propagate through the slab and exponentially decay outside of the slab. These modes can basically be TE polarized, where the electric field is in plane, or TM polarized, where the electric field is out of plane. So below, you can see the computed dispersion relation for the guided mode supported in a 270 nanometer thick silicon nitride slab. Here you can see that one branch of the TE and one branch of the TM modes is supported. If you look closely, you'll see that for the TE branch, basically the dispersion relation becomes highly dispersive, close to a frequency of 0.1 electron volts, which corresponds to a wavelength of around 12 micron. So this indicates that there's a higher density of these guided modes near that wavelength. What's interesting, though, is when you compare this dispersion relation to the computed spectral conductance between our 270 nanometer thick devices. As you can see, the spectral conductance is also peaked at that same frequency of 0.1 electron volts. So because of that spectral match between these two plots, that allowed us to conclude that it's these guided modes that are the specific modes responsible for these large enhancements in heat transfer. So it turns out that regardless of the thickness of these nanomembranes, they will always support one branch of the TE and one branch of the TMOs, regardless of the thickness. And this is completely not accounted for by Planck's theory, which assumes that the electromagnetic modes in a structure are completely confined by its geometrical dimension. So that would essentially underestimate the photon density of states that are present in our nanomembranes. Also, the orientation of the nanomembranes is very important. So on this slide, you can see, I want to show you that we computed the directional emissivity of our emitter membrane as a function of polar angle theta. So in this case, the emissivity was computed as the ratio between the time average pointing flux in a given direction to the black body pointing flux in that same direction. And that was computed along this dashed line here. Okay. So in the bottom polar plot, you can see the directional emissivity plotted for our thickest membrane, which is over 11 microns thick. As you can see, it essentially emits like a black body. The emissivity is close to 1 and it's independent of direction. But for the thinnest membrane, 270 nanometers thick, you see a large enhancements in the emission in the in-plane direction and a suppression in the emission in the out-of-plane direction. So because the emitter and the receiver are coplanar with one another, you see these large enhancements in conductance because that's the direction where the emission and the absorption are maximized. Now, these insights actually gave me an interesting idea for a follow-up study where you can achieve a radiative thermal switching using these nanomembranes. So the approach relied on introducing a third nanomembrane to the system, which is parallel to but vertically offset from the emitter and the receiver by some vertical gap, which I'll call D. So I found that by reducing this vertical offset, I could actually suppress the radiative conductance between the emitter and the receiver. So this is not expected based on a naive understanding of Planck's laws, because essentially the geometrical view factor between the emitter and the receiver isn't modified at all by the presence of this third nanomembrane. Okay, so in the center here, you can see electron micrographs of the emitter and the receiver I used in this experiment, as well as the third nanomembrane below, which I call the modulator here. So in this case, all three nanomembranes are comprised of silicon nitride, and they're 500 nanometers thick. So under high vacuum conditions, I could then precisely align these three membranes in the configuration that you see here, and then adjust that vertical offset D with the piezo actuator. So here you can see the central results of this experiment. Here, the radiative conductance between the emitter and the receiver is plotted as a function of that vertical offset. And here you can see that we essentially are able to adjust that offset in steps of 250 nanometers until contact. And basically, when we reduce the gap size from around 18 micron to 3.5 micron, we could suppress the radiative conductance by a factor of around 2.8. Now, this result isn't only limited to silicon nitride. We repeated this experiment with a modulator that was coated with gold. And you can see the results for the gold-coated modulator on the right here. So with this case, we can actually achieve even better switching ratio with a factor of around 5. So what's the mechanism here responsible for this switching effect? So if you look at the plot on the left, this is the computed spectral conductance between our emitter and receiver as a function of frequency. So initially with a large vertical offset of 20 micron, the spectral conductance is peaked near a frequency of 0.075 electron volts over here. So that corresponds to a wavelength of around 16.5 micron. Now when the vertical offset is reduced to around 3 micron, you see you get a suppression in the spectral conductance everywhere, but especially at that peak frequency of 0.075 EV. So I want to draw your attention now to the plot on the top right. So this is the computed spatial distribution of the pointing flux in our three membrane system. And I should note that this pointing flux was computed at that single frequency of 0.075 EV. So in this case, the emitter, we introduce thermal sources of radiation onto the emitter, so it starts emitting. Here, the red color corresponds to the pointing flux in the plus X direction, and the blue coloration corresponds to pointing flux in the minus X direction. So with a large vertical offset of 20 micron, the pointing flux occurs largely in plane, and a large fraction of the energy from the emitter is transferred to the receiver. But when the vertical offset is reduced to 3 micron, you see that the Poynting flux is no longer really in plane. It actually starts leaking into the modulator below, and actually less of the energy is transferred to the receiver. So the net result is that you get a suppression in the radiative conductance. So basically, you get this leakage of the Poynting flux due to the coupling of the guided modes supported in the top and bottom membranes. And this is possible because the mode tails of those guided modes actually extend several microns into the vacuum on either side of the membrane. What's interesting, though, is that you get a slightly different physical mechanism with the gold-coated modulator, which you can sort of see in this with this Poynting flux map on this slide. So with the gold-coated modulator, it essentially cuts off the mode tails of those guided modes, and those modes are no longer supported by the emitter and receiver. So as a result, they essentially scatter into free space, which you can kind of see here. They're scattering above the membranes. But the net result is the same. You get less energy is transferred to the receiver, and as a result, the conductance drops. So on this slide, I also want to demonstrate that we could achieve an active switching using this approach. So in the top panel, you can see a time trace of that vertical offset between our emitter and receiver and the bottom gold modulator. So here the gap was modulated from 14 to around 2 micron with a period of 2 minutes. And on the bottom panel, you can see a time trace of the radiative conductance, which here is switched on and off with a switching ratio of around 5. So I think in principle, this switching ratio can be further improved, and also think the switching time can be further improved. In principle, it's only limited by the thermal time constant of the nanomembranes, which in this case is actually a lot smaller than 2 minutes. It was around 100 milliseconds. Okay. So I'm almost out of time here, but I want to end by discussing some emerging trends in this field. There's obviously a lot of questions left in this field that haven't been addressed in the works that I just presented. I think in general, researchers are very interested in exploring the fundamental limits of these semi-classical laws of thermal radiation like Planck's law. So one example of this is the idea that you can actually violate reciprocity using magneto-optic materials in the presence of a magnetic field. And this is sort of illustrated on the left here. Other researchers are interested in developing nanostructured thin films which can improve the coherence properties of thermal emission. And this is illustrated if you look at the center rendering here, where you have this thermal metasurface that's thermally emitting light that's collimated and circularly polarized. So this is not currently possible. Also, I think in general, researchers want to develop ways to actively enhance and route thermal radiation, just like you can in an electrical circuit. So an example of that is shown on the right here. So the idea is that you can actually actively tune near-field radiative heat transfer by electrostatically gating plasmonic thin film or two-dimensional material. So I think all these are very interesting ideas, and I think they're ideas I'd be interested in pursuing in the future. I also want to end by introducing you to my research program at UW-Madison. So right now I have a small team of researchers that I work with. Changxing, Xinchao, Qifan, and Yan are my grad students, and together we're developing some unique instrumentation that allow us to make further advances in this field. Briefly, we're developing core expertise in a measurement technique called spectroscopic ellipsometry, shown in the middle here, which allows us to measure the optical and infrared properties of thin films. So as an example, you can see we recently measured the complex refractive index of a sputtered gold film in the visible. We're also developing core expertise in an optical thermometry technique called thermoreflectance thermometry. So below in the bottom right, you can see a picture of this laser optic setup we've been developing. And the top picture, you can see basically our focused laser beam on this metallic transducer. So I'm mostly out of time, so I'll stop there. But I'd like to end by thanking my funding agencies that are supporting me, NSF and ONR. And I just want to thank you all for listening as well. And happy to take any questions at the end.
All right, thank you, Dakotah. Really fascinating results. And thank you for your clear explanations of these phenomena. I have a number of questions. We'll wait until the end here, I think, to get the discussion going. Okay. I'm sure some audience members have questions as well. But now we'll move on to the next talk. Professor Tian Li from Purdue. You can go ahead and share your screen. Okay. I'll do an introduction here. So Professor Li is an assistant professor at Purdue University. and she received her PhD from the University of Maryland and also did a postdoc at Maryland. So her group is right here, beautiful, an overview of her work you can see on the screen there. Professor Li also has received a number of awards, including a Forbes 30 Under 30 award a few years ago. That's very exciting, as well as the ASME Hythorne Waite Foundation Award, I believe, for young faculty. So we're excited about your talk as well. Go ahead, Tian.
Yeah, thank you very much, Matt, for the kind introduction. Yeah, thank you very much, everyone, for coming. So, okay, so the title of my talk today is the Redesign Natural Material for Energy, Water, and Environmental Devices, which is short for Renewed, which is kind of like the name of my lab right now. So I joined Purdue University and the School of Mechanical Engineering in 2024. So it has been almost 2 years now. So I'm very happy that I have the opportunity to present to you, some of my previous work where I was a postdoc at University of Maryland, and also a couple of new works that we initiated after I joined Purdue. All right, okay, so, oops, my screen got stuck. Are you seeing my screen right? Am I sharing the right screen?
Yep, this looks good, thank you.
Cool. So yeah, so this is 17 Sustainable Development Goals by the United Nations. And with all these development goals, the role of raw material is essential, because raw materials, they are the critical parts for the overall economic growth and well-being, and they contribute to the Sustainable Development Goals in one way or the other. And if you think about the production of the material, like they can generate a lot of environmental and social impacts, especially if you're considering the whole value chain, for example, start from material extraction, manufacturing, and use, and end of life. So wood, like here, is a very natural material, natural carbon sink material. And the way trees grow is that it takes the solar energy and it grabs the carbon dioxide from the air via a photosynthesis process. It converts that carbon into biomass, like in this case, like cellulose, hemicellulose, and the lignin in wood. And if you take a piece of wood, just cut it, and take it under a SEM, for example, you would see all these amazing channels inside. They're almost look like they're aligned. They're hollow channels, and they're aligned along the wood growth direction. And on the wood cell walls, there is numerous aligned cellulose nanofibers. So this material, like to us, it has this naturally occurred nanostructure. It's sustainable, carbon neutral, economical, and abundant. So, and also cellulose, like by the way, is the most abundant biopolymer on Earth, cellulose over here. So then definitely sustainability is one of the reasons like why we are so passionate about this material. And the other reason, as I previously mentioned, is that they is further composed of building blocks of different dimensions. So this is a schematic showing that like this is a piece of wood, and if you keep zooming in, it has all this amazing multi-scale aligned structure down to the sub-nanometer scale, down to the molecular chains. Within each of the elementary fiber of cellulose is further composed of this aligned molecular chains with a spacing of less than 1 nanometer. So this material, it's nanostructure. You don't need to actually go to the clean room to define the nanostructure. It's already there. It's so abundant, and you can use it as building blocks of various dimensions. Like for example, you can use it as a micron scale building blocks, nanoscale building blocks, or even sub-nanometer building blocks. So it's kind of like playing with Legos, right? So when you have those kind of multi-scale building blocks, you build things from them. And during my postdoc, we were working on using this material towards advanced functionalities and advanced optical, thermal, fluidics, and mechanical properties. So it's also worthwhile to mention that it's had a great synergy and interaction with the existing industry. Like for example, we have wood industry, we have a paper and pulp industry, we also have textile industry, because cotton, like cotton as a traditional textile material, is composed of 90% of cellulose. It's also everywhere in the daily product. Like for example, it's in your ice cream to stabilize the texture. It's in the personal care, like cosmetics, like in like the cellulose fibers can form a very stable network to hold the additional materials there, and also in adhesives, paints, engineering plastics. So considering its many economic and environmental benefits, we are using cellulose as a very unique framework featuring hierarchically aligned structure from meters tall down to the angstrom scale. And recognizing this potential, we have evaluated cellulose as a sustainable technological material and demonstrates new phenomena in microfluidics, nanofluidics, molecular scale transport, as well as advanced mechanical, optical, and thermal properties. So this is a framework of materials truly enabling applications across length scale. Okay, so Renew is the name of my lab right now. We were looking at energy generation, energy part, energy generation, thermal and optical management, energy water interaction, and also devices. Like devices include ion regulation device, biomedical device, and so on, wearable device as well. So our long-term goal here is to try to apply the fundamental knowledge in heat and mass transfer and in thermodynamics to establish this material toolbox. It's a toolbox of natural material for energy, water, environment, and devices. So this is a rough, kind of like a group of my previous work on engineering the wood towards a sustainable build. So buildings consumes around 40% of the total energy in US. So energy efficient building materials can help to largely cut down the energy usage. So the development of technology has to be aided by the advances in material design. And we offer a material perspective. So here are the 3 representative work of mine during my postdoc, including thermal insulation wood, where we have a highly porous wood with a thermal conductivity close to that of air, while maintaining the structure, like the load-bearing characteristic of wood. And this one is a transparent wood. We remove the colored part of the wood so that the light won't get absorbed. And then we fill in the optical refractive index matching material into the pores of wood so that light does not get scattered and reflected back. So this way, the incoming light, in the visible range does not get absorbed and does not get reflected back. It gets transmitted through. So this is the work that I'm going to put a focus today, radiative cooling wood. What we're doing here is we strip the color like from the natural piece of wood. So this piece is directly processed from this one right here. It's a natural piece of wood. And it shows a sub-ambient radiative cooling performance within a 24-hour period. Okay, so when we're talking about energy, so I'm teaching sustainable energy for this semester's graduate level course. We were looking at different energy options. When we're looking up to sky, right? So there's a sun, which is our primary energy source. So there's often a neglected energy source is actually our blue sky. So if we're looking at the energy radiative heat, well, the radiative heat transfer between the sun and Earth is the efficiency limit is dominated by the Carnot efficiency. It's the 1 minus temperature of cold, which is the temperature of Earth, over that temperature of hot, which is temperature of sun. So you have around 1 minus 300 over 6,000, you have around 95%. So when we're looking at our universe is our ultimate heat sink with a temperature as low as 3 Kelvin. So if we're looking at the Carnot efficiency for the radiative heat transfer between the Earth and the outer space is 1 minus 3 over 300. So that's 99%. So it turns out to be a rather efficient process. So if we want to use our universe as our outer space as heat sink, we need to look at what is connecting between the Earth and the universe, and that is our atmosphere. So when we're looking at the transmission spectrum, this is the transmission versus the wavelengths in the IR range. And you would immediately notice that from 8 to 13 micron, the transmission is almost 1. And we call this atmospheric transparency window. When Earth is radiating as around 300 Kelvin black body, which means that when the radiation is within 8 to 13 micron, it gets transmitted through. So in theory, anything that is strongly emitting within this range will be able to get a cooling energy or cooling power. So daytime radio cooling has been challenging because whenever the object is facing to the sky, it is facing to the sun as well. We're developing this. We developed this cooling wood, and we're trying to strip the color from it because the pigment will naturally heat the object up. The color in natural wood is actually lignin. And with this is we extract the lignin and do a spin coating, and you will see that the absorption peaks lies within the visible range. We use some chemical-based treatment, and it's worthwhile to know that these chemicals are commonly used in papermaking industry to strip away lignin, the colored part. So this is what it looks like, a natural piece of wood. So after the chemical treatment, it becomes white. Okay, so we're also trying to preserve the mesoporous structure of wood, because when we have a like the pore size around microns range, it can effectively backscatter the incoming light. We are also looking at the infrared emission of wood by having FTIR measurements. Due to the molecular stretching and vibration, so there's very intensive emission around 9 micron, which coincidentally lies within the atmospheric transparency window. So this is what the spectrum looks like. We are plotting it from the UV to the visible range to the mid-IR, as you can see. So this is a broadband infrared emitter. It's almost non-absorbing under the solar spectrum, but it's heavily emitting in the mid-IR range. And we're observing a cooling effects continuously in 24 hours. And it's also worthwhile noting that this material, like after physical densification, that it actually features a quite good mechanical strength. The wood cells after densification, it collapses and provides a physical entanglement. And the aligned cellulose fibers inside has a maximized interaction of the hydrogen bonding, and it features a 8 times enhancement in the tensile strength. Okay, now I'm going to switch gear a little bit and talk about the cellulose multiscale fluidics phenomena. So trees, they are natural energy water system. So the wood trunk is composed of all these numerous aligned fibers along the wood growth direction. They're responsible for the water and ion transport from the root to the leaves of the trees for the photosynthesis process. So in this direction, so we have demonstrated a multiscale fluidic phenomena. Like first of all, we were looking at the microfluidic, using wood as a microfluidic scaffold for a solar steam generation. And then we went one scale smaller, and we were looking at the ion regulation based on a nanofluidic effect. And then we went one scale lower. We opened up the molecular chains within the elementary fiber of cellulose, and we observed a new like transport phenomenon of intercalated sodium ions in this. Okay, so but the focus of the talk today is actually this one. So along with this direction, so after joining Purdue, with the, like currently I'm in the academic area of heat and mass transfer and thermodynamics. So this is our first project working on the interface of water and heat transfer. So we were using a radiative cooling fabric for ambient water harvesting. How it works is that you would have a fabric that had a cooling performance, and you can just unfold it and face to the sky for the water collection. And then after the fabric had the water inside, you can just fold it back and squeeze the water out. So this like just like wood, like fabric, which is mainly cotton fibers inside, features a multi-scale arrangement of the fibers inside. As you can see, then we have the micron scale fibers, and each of the fiber actually is further composed of all these aligned nanofibers inside. And they feature mesoporous structure, so that's the reason why it looks very white. And we want the whiteness for effective radiative cooling performance. And all these entanglements that you are looking at, SEM here, it provides desirable mechanical strength, right? So it can sustain over many cycles of water collection and extraction by mechanical squeezing. So how does heat transfer get involved in this? Like why this is a water energy interaction? So there are two dominating mechanisms, like grabbing water from the air. So that is absorption and doing. So absorption, there's adsorption where the water gets attached to the porous scaffold, and there's absorption where it can go past the interface. And there's doing as well. During the absorption process, it's a exothermic process, means that it's released heat. During the doing process, you probably have this from your daily experiences. The outside of your ice cold coffee is going to have condensed water there. So absorption and doing, they naturally are coupled with heat transfers. And in this project, we use a radiative cooling fabric. It's the cooling, like the passive cooling, like you don't have to have any energy input to it. The passive cooling, it spontaneous happens by facing the fabric to the sky. And this cooling helps with both absorption and doing. It facilitates the absorption process and lower the saturation vapor pressure so that it can promote condensation. In turn, after the cellulose fabric grabs the water to it, water actually enhances the infrared emission so that it can promote a stronger radiative cooling effect. So this truly gives us a positive feedback loop of like for a desirable performance. So this is actually an image of the group members are holding several pieces of the fabric. And as you can see, so this is the photo image and this is the IR image. It features a much lower temperature compared with the ambient. And we're looking at a similar, similar electromagnetics responses here, where the material features a low absorptivity under the solar spectrum and a high emissivity in the mid-IR, especially from 8 to 13 micron. So we characterize the performance. This is actually some field test data, and this is actually lab test data. As you can see here, in the low RH relative humidity region, absorption is the dominating mechanism, while in the high relative humidity region, doing is the dominant one. So when we were looking at these results, and then we realized that, okay, so when the doing is dominate, the performance is not bad. But when we're looking at absorption dominant one, for especially dry regions, the performance needs further improvement. So like because of the challenge here, like we wanted the material to be working in all weather conditions, even in dry regions, right? So because dry regions are the regions that need the technology. And we were trying to incorporate salt into the cellulose fabric. The process can be very simple, right? So it's you can just have a cellulose scaffold like a fabric and soak it in a salt solution and then dry it. Right, so we were trying to use the salt. We pick a salt that's quite good in absorption, we pick this salt to trying to boost the water harvesting capacity as well as the kinetics, and so that the working range of relative humidity can be extended. And we hope that, well, cellulose can provide the mechanical support to retain the water and the salt solution. So, and then we use the SEM and element mapping to look at what's really happening inside. This shows nicely that the salt indeed get intercalated among the fibers. And by doing a cycle performance to look at the sample mass, the cellulose fibers can, the same set of cellulose fibers can well confine the salt and the salt solution, and very well disperse the salt and prevent the salt agglomeration. So we were looking at the kinetics as well as the capacity of this new composite material, the cellulose salt composite material, and we observed both a higher rate of water absorption as well as a larger capacity of the composite compared with just these two added together. So this shows some synergistic interaction between the cellulose material and the salt and the salt solution. This is a comparison with the current technology, like current materials for ambient water harvesting. It seems that but after incorporating the salt here, we were able to extend the working range to as low as around the 10% of relative humidity. And we're indeed looking at a pretty good performance. Our curve is actually the black one here, and here is the dashed line right here. Okay, so that wrap up my talk. So we trying to establish some, I'm very fortunate, after I joined the Purdue, our colleagues are extremely friendly, and we established some very meaningful collaborations, both within Purdue, within the mechanical engineering, and outside the university as well. Okay, that wrap up my talk, and welcome any questions.
All right. Thank you, Tian. Very interesting. The materials you're developing are really quite novel. So I'm excited to discuss. So I think first here we can call Dakotah back to the stage as well. Dakotah, hello again.
Hello again.
So I'd like to first open up for any questions for either of the speakers from the audience, and then I think it'll be good to engage in some discussion, maybe about how some of the concepts introduced in both talks kind of are cross-cutting. I have some thoughts on that as well. So are there any questions from the virtual audience here? If not, I do have some for each of you. So for Dakotah first, I'm curious specifically in the context of your work, how, well, I'm sure you've thought about this in detail. What are some applications potentially of these nanoscale modulators? I guess it's like a thermal transistor almost. Yeah. I'm sure you've thought about this. I know there's discussion in this field about this. I'd like to hear your thoughts on some application areas for that sort of device.
Yeah, I think one of the things I was thinking about is maybe it could be useful as like a tunable glow bar for some like a FTR microscope or something. So it's basically like a tunable filter almost. And I didn't really show those plots, but when you adjust the gap size from the modulator to those devices, you also change the radiation spectrum, the heat transfer spectrum between them. So maybe it's a way you could. So right now glow bars in FTIR microscope are just like a wire of tungsten or something like that. But maybe it would be useful to have one that was actively tunable, so you could span different wavelengths that you couldn't before. Something. So I think maybe something like that, or I think with different types of sensors like bolometer detectors, you could get one that you could tune its sensitivity to different spectral regions and things like that. And so. Yeah, those are kind of two thoughts I had.
Okay, yeah, that's interesting. I'll quickly say, if there are any other questions from the audience as we go along here, feel free to speak up or put your thoughts in the chat, and we can talk about that. I want to follow up with another question. This may be completely off base. I may be thinking about this the wrong way, but I'm curious. Are there any ways to tune the radiative heat transfer and the devices that you showed without physically moving, like physically moving the a specimen, or like through a flow field or some other sort of mechanism?
Yeah, I think that's a great question, and you're right. It's I think you want to achieve like some active rectification or switching without moving something mechanically, and so there are ways you can do that. I mean, there's basically there's ideas that you can use applied magnetic fields with some magneto-optic materials, and you can use that to tune the heat transfer. You can some materials you can tune their chemical potential of a material, like a graphene or something, by applying an electrostatic field, and that can tune the heat transfer as well. There's thermochromic materials like vanadium dioxide that people are interested in my field. So vanadium undergoes like a phase transition, metal to insulator phase transition, a little above room temperature, and so that can be used as like kind of like a thermal diode. You can use that to make like thermal diodes for radiative heat transfer. So I think there are a number of ways to kind of like actively control heat transfer without doing anything mechanical. And I think that's where the field is definitely moving. I think people are very interested in that, those ideas. Yeah.
Wow, I didn't even know that. So maybe I should join your field. I could maybe contribute. No, I shouldn't. I'll ask a question for Tian now. So you showed. Thank you for focusing on the thermal properties and the radiation effects from the wood materials you're developing. I think that was very interesting and a good way to link the two talks here. But I actually have a quick question about one of the other properties you showed. You showed some mechanical measurements as well of the wood, I think after delignification. I'm assuming that the mechanical properties of wood are probably anisotropic based on the structures you showed. Does the anisotrope, is that correct, first of all?
That's right, yes.
Okay, so does the strength of the stiffness, does the anisotropic nature of the strength of the stiffness change after you delignify or do the chemical treatment you showed, or is it of a similar anisotropicity, anisotropicity? I guess that's how you say it.
Yeah, yeah, that's a good question. Yeah, so it's definitely anisotropic because like we're looking at a partially aligned along the wood growth direction in all these scales that I was showing. You know, like in the wood cell, which is 10 or 20 microns, like down to the cellulose nanofibers. It really depends. Like for example, if we're looking at the tensile strengths, like the factor of tensile strength in the two directions before and after the lignification. It really depends on the wood species and the degree of the lignin reduction and also the degree of the densification. It's a competition, like because it's a competition between the molecular bonding, the strength of molecular bonding in the cross growth direction and the long growth direction. So this is stronger because it has a very strong connection of the glucose units along the molecular chains.
Okay, great, thank you. Siddhartha, I see you've joined us here. Do you have any comments or questions?
I mean, I've closely worked with Tian, so it would not be appropriate. We have written multiple publications together, so it will not be appropriate for me to ask questions to. I mean, no, it's so I'm aware of several of the things that Tian showed. Maybe as just like a follow up, like not a question but an inquiry, more importantly. So Tian, I mean, are there like any kind of like, I know whenever you wanted some kind of a charging thing, there was like tempo treatment, if I may.
That's right.
Right. So beyond that, are there ways to put or like to have some kind of engineering of the charging of these channels, of the nano channels beyond that?
That's a good question. So previously we've tried like tempo, that's the important one. Like we changed from OH group to COOH, like hydroxyl to carboxyl, which dissociate more easily in water. And there's definitely other functionalization you can do to the surface charge of cellulose fiber. We like typically it's negative because of the deprotonation process,
Right,
but
right.
also make it positive. There are, like recently we were developing this coordination of ions, which will change the surface charge density as well.
Right. Yeah. So one challenge, Matt, that I can give you a sense in this discussion. So I've worked extensively with Tian's former advisor, Liang Binghu.
Yes.
So is that one major challenge is the extent to which you can control the charging. As for example, if you compare that with, let's say, a silica nanochannel, there you have like significant amount of control. Obviously, you gain so much other things with a nanocellulose, 100%. So that far outweighs as compared to what as compared to an actual fabricated nanochannel. But in terms of like, if you just think about how we can engineer the charges, for example. Or let's say we want a high zeta potential, or you want that kind of a control. Let's say you want some kind of a distribution. It becomes a bit of a challenge. And Tian can correct me on that. That becomes a bit of a challenge.
That is correct, actually. So the chemical treatment of cellulose is a kind of there's a concern of the uniformity of the treatment. Like for example, well, if you are able to treat every single nanofibers, then definitely you will have a more uniform performance and potentially better outcome, like for the like surface functionalization. But
Exactly.
we're looking at the fiber bundles. So it's like because there's a diffusion limit like of the chemicals that like during the reaction, uniformity has been a challenge.
Yes.
So currently like the surface charge density we're looking is it just has a little bit very partial dissociation of the hydroxyl functional group. Like in theory, if we're able to, like for example, get rid of all the hydrogens, like it's definitely going to have a higher surface charge.
Right. But as Tian rightly points out, and she's an expert on this non-uniformity can be a big problem. Let's say if you would like to use that kind of a nanocellulose as a reusable, maybe some kind of a capacitor or some kind of a transistor, as people do with nanofluidics, for example, standard like a engineered nanofluidics, like silica-based nanofluidics, then in context of that, this will be an issue.
Right.
Yeah. So this is a general issue, like when we are using like a bulk chemical treatment to like treat a cellulose-based product, like because like for example in some other nanofluidic channels, like we have a more careful fabrication process of the material, either self-assembly or using even lithography to etch it carefully. But for this material, because the nanoscale features, they're already there, we just directly gonna to treat it like in a bulk method. So that's kind of like a general issue in the treatment of the cellulose fibers. Like of course, like if we can choose to use a mechanical chemical fibrillation method to like break the fibers down to smaller dimension, and then have the chemical treatment there to ensure a more uniform like outcome.
Exactly.
Got it. Let me interject here. Sorry to break up this interesting discussion, but Stephen, one of the audience members, has a question for Dakotah in the chat. Dakotah, I don't know if you can see that, but the question's about the dependence of the extent or depth of the thin films on heat transfer enhancement, I think in the structure you showed, as well as thickness effects and alignment effects. So maybe you can address that.
Yeah, it's a great question, Stephen. So the depth of the membranes in the in-plane direction is also very important. And we in the paper we did some simulations to investigate that effect. Basically, once you're you have to be your membrane has to be longer than kind of the penetration depth or the absorption length of that guided mode along the membrane. So as long as you're longer than that, then you can get large emission and absorption. But if the membrane starts getting too short, it's not going to absorb as much as it could. So I think we found for the silicon nitride, as long as the depth was over like 50 micron, you kind of get diminishing marginal returns there on the, the enhancement and heat transfer you can observe. Also, the alignment is important. And we did a control experiment where I fabricated a version of these membranes that were actually tilted by 11 degrees. And interestingly enough, when they're tilted, actually the radiative heat transfer goes down. Like the measured conductance drops, which is kind of counterintuitive, because you would think if they're more tilted, the view factor will be larger between them, but they actually don't emit very much in the out of plane direction. So because they're tilted.
That supports your, I guess, the mechanism that you're proposing, right?
Yeah, that's right. Yeah. So yeah, we did that control experiment as well. Yeah. So yeah.
Very interesting. Okay, I have one more question that will kind of bridge. I hope will bridge both of these topic areas, and it was inspired actually by a senior design class that I'm involved in here at Georgia Tech. There's a team that is trying to design a house that is self-sustaining and doesn't use air conditioning. And ideally would have some sort of responsive insulation, right? Or be able to transfer heat when it's needed versus retain heat when it's needed, and not have to use heating and cooling, right? So I'm sure, this concept is not new. I think a lot of people have thought about this, but I would like to, based on both of your expertise in the area of thermal radiation, heat transfer, and materials, what sort of new ideas are out there, or we could think up maybe that would be like dynamic insulation for houses to reduce heating and cooling loads?
Yeah, that's a good question. We actually have
maybe it's a terrible idea. I don't know, but I'd like to hear your thoughts.
So the application is real. Like there's truly a need for that. So we actually have a 2 active projects like in my group right now in this direction.
Okay.
Either control the heat flow, like for building envelope material during winter or summer when it's cold and hot. We want the heat flow direction to be different. And the other one is kind of like a dynamic or adaptive phase change material that can cool when it's needed and get heated up when it's needed.
Right. So like a thermal storage material that can be integrated, right? Yeah.
So it's kind of like a combination of radiative cooling, and then it's a phase change material. So when the temperature is low, when the cooling is undesirable, it's switched to heating. So, but it's kind of like not exactly the insulation, but it's
Yeah, I think a lot of the opportunities are probably with window design, right? So kind of designing adaptive windows, using some of these thermochromic materials, or Tian's materials seem very relevant for that kind of thing.
Yeah, that makes a lot of sense. I guess from your perspectives, is this an important area that deserves more focus in the area of thermal engineering? I mean, there's a lot of focus now on building efficiency in general, kind of in the US, to improve the usage of energy. And I would assume that thermal engineering is a really big part of that, but I'd like to hear your thoughts.
Yeah, I think we can go a lot further. It's funny that, this passive radiative cooling is something that I've read about for a few years, and it's definitely like very hot topic in the field. And I think it started by these people, they wanted to make these like nanostructured, like thermal metasurfaces. And I think researchers have gotten smarter and have learned that you can do it without lithography, and which I think is important for scaling up. And I think in the future, we're going to just try to make these radiative surfaces more active. So can you actively control them? So I think that's kind of the next maybe evolution. I'd be interested in hearing Tian's thoughts.
Yeah, so I definitely like right now for building envelope material has draw a lot of attention, for in order to improve the building energy efficiency and the thermal management, control of heat and mass transport there has become a very hot topic, and I think it deserves to be, because like you're right. There's a lot of material that people are looking at, like to be used as a building envelope, and they are looking for ways to scale them up. This is actually also like it's funny, also related to why we are passionate about like cellulose wood-based material for such applications, because wood is like a traditional use building material, right? So with kind of like a little bit of twisting, like a little bit change of the material morphology, the composition, and now it has this advanced thermal management capability. And now it's still based on wood. It's still very cost effective. But now it can be used to saving more energy.
Yeah, that's a really good point, Tian. I think when you think of these potentially more exotic solutions for dynamic control of thermal properties, you're always competing with, fiberglass and wood that's used in real buildings. And so considering costs and strategies of that sort, I think is really important. So that's a very good point. Great. Well, this has been a great discussion. Thank you both for joining us and giving us an overview of your research areas today. If there are any more questions, we'd be happy to take those. But if not, we can end a few minutes early here and let everybody have a happy Friday afternoon. Oh, Siddhartha, you're muted here.
Yeah, thank you, Tian. Thank you very much, Dakotah. It was wonderful listening to both of you. Okay, good.
Thank you so much.
Have a wonderful weekend.
Thank you, Sasa.
Yes,
Thank
thanks
you.
very much. Have a good weekend.
Take care. Take care. Bye. Bye.
See you, Tian.